So Miss Wu and I went golfing, and before every shot, she would whisper 24. And I got curious and I said, Miss Wu, why are you whispering 24 before every shot? She said, well, I have a sore throat and I can't yell 4. Get it? 4 factorial is 24. And if you don't know that now, you'll learn it as we do this lesson today. All right. So one way to figure out how many outcomes there are tree diagrams. But here's the good news. I'm going to do this one tree diagram with you, and then I'm going to show you some other ways. Now, that's not to say that you're never going to want to do a tree diagram again, because they're incredibly helpful. But sometimes there's just too many outcomes to really make a tree diagram. So we're going to make a tree diagram for the 4 letters in Word. How many ways can I arrange that, where I use each letter once? Well, I have 4 choices for the first letter, and there they are. Then I have 3 choices for the second letter, depending on which one I pick. Then finally, I have 2 choices for the third letter, and then 1 choice for the fourth letter. And then here are all the outcomes. All right. If I count all these possible outcomes, then I see that there are 24 ways to rearrange the 4 letters in Word. What if I compare it to the products for these? It's 4 times 3 times 2 times 1, which is 24, which kind of shows us that we can just multiply the number of ways we have to do something. So a factorial is a special product of the integer and all the positive integers before it. And this is how we get it. 4 factorial would be 4 times 3 times 2 times 1, which is 24. Then 9 factorial is even longer. It starts at 9 and goes all the way to 1. And it's 362,880. Now, if I asked you to do something like 15 factorial or 10 factorial, you might go, oh my goodness, that's a lot of numbers to enter. So the good news is on your Ti84, you can actually do factorials. First, you enter the number. In this case, I have the number 9. And then you press math right here. Okay. Then you arrow over to PRB right there. And then you arrow down and either press 4, or you arrow down to this line and then press enter twice if you arrow down. All right. So if we did the calculator and did 4 factorial on it, we would get 24. And you can see here I have 9 factorial and I got the same number, 362,880. But not all problems can be done super easily with just a factorial. So how many ways can you arrange 10 letters with 15 different letters to choose from? You might say, oh, it's going to be 15 factorial. But the thing is, I'm only using 10. So the number of ways is how many ways I can pick for the first position, then the second, then the third, fourth, etc., until I have 10 positions filled. So when I fill them in, it looks like it's getting close to 15 factorial, but not quite. So how could we do this with 15 factorial? So I'm going to say the number of ways. Let's pretend it was 15 factorial for just a moment, so I can write all that out. What's wrong with this? Why is my answer not going to match? Well, it's these numbers back here because I don't have 5, 4, 3, 2, and 1. So how could I make this answer be the same as this? Some people have been tempted to say, well, you could subtract 5 factorial. Actually, it doesn't work that way. But if I divided by these numbers, which is 5 factorial, then that does give me the same answer. So you can take the number of things you have to choose from divided by the ones you don't choose, how many you don't choose. So where do we get that? 5 is 15 minus 10. We have 15 to choose from. We take 10. That leaves 5 left over. So permutations represent the number of ways you can arrange n items with a total of r choices to make. We're going to write an expression to calculate the number of permutations using n and r. So we're going to go ahead and write that formula out. N is like 15 in our example, and r is like 10. And here's the formula, NPR, where you have it's n factorial over how many you didn't choose factorial. Okay? So on the Ti84, good news, you don't even have to do the factorials and divide them. It will spit the answer out for you. So you enter in the number for n, then you press math again, go to PRB, press 2, which is also that NPR, Enter in the number for R, and then, by the way, you might see X instead of R in some of your assignments. And I know AP Stats, we tend to use X instead of R, but they basically are the same thing. Then press Enter after you've done that. Now you'll notice here's the answer, and I have this 1.0897 e to the 10th. What the heck is this? Well, when I get a very large number, we can use something called scientific notation. And the way your calculator does it, it says, oh, this e stands for the exponent on 10. So this is 1.0897, etc., times 10 to the 10th. So how could we write that as a normal number, not in scientific notation? Well, you're going to move the decimal 10 places. And in this case, we're making the number larger. Okay, so it's to the right. So how many different 5-digit numbers can you create from this number right here? The secret to these is making sure you have the right N and R. So N is 9 because there are 9 digits to choose from, and you're going to take 5. All right. If I did the formula like this, that's what I would do. I could actually enter this in the calculator or the right side. Either one will give me the answer of 15,120. How many different 4-letter arrangements can you make from the word ambidextrous? Well, there are 12 letters here to choose from, and we're going to take 4. So it would be 12, 4 right there, and if you run that on your calculator, or you could go 12 factorial divided by 8 factorial, which is 11,880. Let's go ahead and look at a different problem now. Braden, Ellie, Michael, and Zach are all applying for 2 lifeguard positions at the YMCA. How many different ways can they pick the lifeguards? Well, I could do a tree diagram, but I can also do a list. You're allowed to do lists as well when you're trying to figure out how many ways to do something. So I said, well, I could pick Braden and Ellie, Braden and Michael, Braden and Zach. It's sort of like the top part of a tree diagram. And then keep doing it for each of the 4 first choices. So here I'm counting 12. But let's think about this. Does it matter if I pick Braden before Ellie or Ellie before Braden for the lifeguard positions? No, because they both get the job, and it's not like they're different jobs. It's the same type of job. So I'm going to start getting rid of some duplicates, like Ellie and Braden I already have because I have Braden and Ellie. This is unique. That's unique. Michael and Braden. Oh, that's Braden and Michael. Michael and Ellie, I already had Ellie and Michael. And this one's new. And then the rest of these are all dupes. So really, there are only 6 different ways to pick them. Would I get 6 if I used a permutations formula? No, I'm actually going to get 12, which is the original 12 here. All right. How could I fix it so I can figure out how many get the 6? Well, how many different ways can I order this choice of Braden and Ellie? There are 2 ways, because I have 2 choices for the first and 1 for the second, or 2 factorial ways. So if I modified my formula, where I divided it by 2 factorial, the number of ways I can rearrange every answer, because it's double counting in this case, then I get the right answer. So in permutation problems, order does matter, and it does not matter for combination problems. So let's go ahead. Drawing 5 cards from a deck. Let's say you're playing poker. It does, and you don't bet till, after you get your 5 cards. Well, in that case, order doesn't matter because you can rearrange them in your hand, and that doesn't change how well you're doing. So that's called a combination. Picking batting order for a softball or a baseball team absolutely does matter. And so order matters, so it's a permutation. Officers for a club. President is different than vice president, so the position or order does matter. Picking flowers for a bouquet doesn't really matter, the order. Or 2 books for a trip, if you're just going to throw them in your suitcase, you can pick out whichever one you want to read first later. But just picking 2 books for a trip, it doesn't matter which order you pick them. Seating assignments. Definitely would say that order matters. In my room, we have the table by the window, and then we have the table on the other ends. We have tables all over. They're different. Numbers on a lottery ticket. Well, I would argue it could be either one, because there are some lottery tickets where you have to do certain things in certain orders, and there are some where if you just pick the right 6 numbers or so, then you win. So it depends on the game. Members of a committee. Well, if they're all equally important, then order doesn't matter. That's a combination. If I'm picking 3 winners for a bag of chips, order doesn't matter either because they all get a bag of chips. They don't care if they get picked first or second as long as they get picked. But if you're picking first, second, and third place, first is different than third, so order does matter. Since order does not matter in combination problems, so you can see with the C's, how can we adjust our permutation formula? Well, the hint is the ones we do pick, how many different ways can we arrange them? That's how many times too much we count. So we actually divide by that, kind of like I showed you with the Braden and Ellie problem. So if I calculate the number of ways you can pick 5 cards from a deck, there are 52 cards in a deck and 5 to choose. Basically, I would write combination now instead of permutation. 52 factorial over what I don't pick factorial, and then 5 factorial, how many I do pick. And I would get 2,598,960 different poker hands, which is actually, I think they published that on the deck or something. All right, calculate the number of ways you can pick 3 free apps from a choice of 10 apps. Well, you have N is 10 to choose from, and there are 3 that you get to pick. So it's 10 choose 3, 10 factorial over the difference factorial, and 3 factorial. And you get 120 different ways. Hard to believe, really. All right. Then let's go ahead and show you how to do this on your calculator. It's very similar to permutation. The only difference, you're still doing N, still pressing math, still going to PRB. But this time, instead of pressing 2 for NPR, you're going to press 3 for NCR. And then enter in the number for R and press enter. And here you go, 10 NCR, choose 3. And what do we see? 120. Now, you can also do this on ClassPad if you don't have access to a TI at home when you're trying to work on problems. So if you go to ClassPad.net, you click on a new paper to get the pop-up. And instead, we've been clicking on this data, but now today we're going to click on calculate, which is the square root symbol here. Then we're going to get a big dialog box, I guess is the best way to call it, or another pop-up. It's going to default to number, but we actually want to be on math. So make sure you click on that first. And then you'll see if you got the free version, you'll see 1, 2, and 3 is grayed out because it's got extra stuff that we don't get to use unless you pay for it, which is fine. Click on the 2. The functions we're using today are free. And in fact, you'll see there's the factorial, there's permutations, and there's combinations. So pick whichever one you're looking for. And today we're talking about combinations right now. So you'll get this dialog box right here. Put in your N and then a comma and then your R, and then you can press execute right there, or even enter should work. And then after it calculates, you can actually keep working on a list and enter in more functions. So you can actually, you don't have to restart from the beginning. You can just keep adding on to this. And that's how you use ClassPad to do combinations and permutations.